I'm going to hold off on this last example until we go through these conclusion questions, and you'll see why in just a minute. We're going to compare the graphs of C and D on the front page. So for C and D, the ones I really want to look at are g sub 1 of x equals 1/4 times the absolute value of x, which we knew was a vertical shrink. And that graph is here, this pink graph on the right. And then on D, we have g sub 1 of x is the absolute value of 1/4 times x. And this was our horizontal stretch. So we've got a vertical shrink up top, horizontal stretch on bottom. And this is the green graph down here on the right. Notice these graphs look the same, and that's because they are. So with absolute values, our vertical shrink is going to look exactly like our horizontal stretch, and vice versa. A vertical stretch will look like a horizontal shrink as well. So we can say that the graph of g sub 1 of x in both C and D appear the same. A vertical shrink or compression by 4 looks like a horizontal stretch by 4. This will be the case with absolute value functions, but you need to note not all of our parent functions will have this property. Especially when you get to pre-cal with your sinusoidal functions, vertical and horizontal are going to look completely different. But in the case of absolute value, they appear to be the same. Okay, so the next question, what can be said about reflections of absolute value functions? And feel free to answer these on your own. If you come up with something that I didn't say, just run it by the sub or Mrs. Salazar and make sure that that's the case for all. Alright, so reflections. We're going to look at reflections. And in C and D is where we saw our reflections. I'm going to highlight using orange. So in C, we have a reflection right here with that negative. And that was the y values becoming negative. So remember, it reflected over the x-axis. And that was this purple graph here. So we get an upside down V shape. Over here in D, we had the negative inside the function, so it's reflecting over the y-axis. Our x's are becoming negative. So we have this graph right there on the right, that pink graph. Now, reflecting over the y-axis didn't actually change what this graph looks like. If it hadn't been reflected, it would look the exact same. So visually, reflecting over the y-axis has no effect as long as there's not a horizontal shift. So as long as you're not shifting left or right. But reflecting over the x-axis obviously shows that our graph, our V-shape, is going to be upside down. So to put that into words, when reflecting across the y-axis with no horizontal translation, there's no visual change to the graph. I'm not sure why there's a parentheses there. We'll get rid of that. And then when reflecting across the x-axis, the shape is an upside down V. Okay, the third question, how can you determine the vertex from the equation? So we're going to look at a couple of these to see that. And I will highlight with this bright green color. Okay, so if I look at the purple graph, we went right 3. My vertex is here at 3, 0. So that comes from shifting right 3. The second graph, we shifted left 5, and here's our vertex. The vertex also shifted left 5. Looking at C, we didn't shift left or right, up or down on C or D, and notice our vertex stays at 0, 0. So it's those horizontal and vertical translations that are going to affect our vertex. Alright, so the vertex is determined by the horizontal and vertical translation as long as the B value is factored out. So by looking at this last example that we haven't done yet, Notice this is a b value because when we're doing transformations, we have f of x equals a times our function times b of x minus h plus k. So as long as this b value is factored out, hk is our vertex. And you learned this back in Algebra 1 with quadratics, and we're going to look at it again several times this year. So that means that our vertex here, my h value is a 2, my k value is a -7. So our vertex will be at 2, -7. And this is the case because that 3/4 is factored out.